First of all, hello to all of you. My name is José-Luis Vilchis-Medina, and I will present, or I'm going to talk about this paper, which is published at IROS 21. And this paper is named Autonomous Decision Making with Incomplete Information and Safety Rules Based on Non-Monotonic Reasoning. And an overview, we have 6 parts. First of all, we have the introduction. Second one, the state of the art. I want to talk very quickly about non-monotonic reasoning or contribution, simulation of results, and finally our conclusions. Well, we talking about a robot, an underwater robot, which has different sensors. For example, bar 3, with which is a sensor. We can estimate the depth. So, for example, we have the MIU, which is another sensor which embeds multiple sensors, which allows to estimate the position in the space. And we have a lot of sensor, for example, a GPS, but this is only useful on the surface. And the echo sounder, or it is just to know the bottom of to calculate the distance to the bottom of the sea, and so on. And so we work with biologists. So biologists use a transect. What is a transect? Well, a transect is a virtual, actually, it's a virtual line from the start point to the end point. It's a straight line. So normally the robot has to go in a straight line, but the environmental change is all this constraint can be derived, and for that we use this approach. This is for example the main normal mission is that the robot starts at the surface. And if the robot has a good single GPS, so the next action is to dive, fixed depth. We call it fixed depth start point, because this is the beginning of the mission. And then one time he arrived to start point, he go to in a straight line to the end point. So this is a transect, or TL. And then the robot go up to the surface to the main ship. And this is a general idea of a transect. So, and the problem here is that the robot has to how can I say that, react to unexpected situation because of change of the environment, uncertain information, sensor failures, or whatever happened in the sea, under the sea. So we propose a solution based on goal reasoning, and this is the basic idea is we apply actions according to the situation, according to the current information, always taking into account the goals and the safety of the robot. So in the literature, we have several papers that attack these kind of issues. For example, non-robot framework, which use a description logic for knowledge representation, and this representation is a central knowledge, and they use product as a classical theorem prover. Another idea is to use answer-set programming, which is a declarative programming based on the state model paradigm, but there are some weaknesses about this language. One of them is that not support free variables, and sometimes it's difficult to debug a program in ASP. For that, I propose from my PhD thesis, where I formalized the behavioral pilot using non-monotonic logic. And thanks to the full logic and prologue, sorry, I built a non-monotonic inference engine. And also, I propose a framework to study of a resonance system using this kind of logic, the full logic. So now I'm turning to non-monotonic reasoning. I just put this John McCarthy and Raymond Rater, because they're the most relevant figures that propose this new formalism, which helps to manage conclusions when we have partial information, or even we have a contradiction as a premise. And the formal definition from Rater, he defined out the default theory, delta default theory, that embeds two sets of default and sets of W, which means defaults is everything that is not known, and W is everything that is known and is represented as a first order formulas. A default has the following form ABC, where ABC are well-formed formulas, and X is a vector of free variables, normally not quantified. Intuitively, a default means that if A is true and there is no evidence that B could be false, then C is going to be true. And I put some example just to clarify why the default is important. Well, a classical example is about Tweety and birds. So in classical logic, we can say that birds fly. Normally, all birds fly. But what about chickens, penguins, kiwis, ostriches, and the list goes on. So a solution is put in a list all the cases or all the birds that do not fly, but that's become very impractical. Impractical in terms of the list can be, yes, it's a finite list, but it's going to be like a very large list. A solution is use the full logic. But now the sentence overflies. We transform a little bit into normally bird fly, and we have a default bird fly. And if we know that the Tweety, for example, is a bird, but Tweety is a penguin, but the penguin doesn't fly, as a knowledge base, we can conclude that the Tweety can fly, because the last rule contradicts the default. So for that is we conclude this like this situation like that. And default for the calculation, for the solution, I'm gonna use the extension. Sorry, for the solution or extension, or the problem here is find the solutions or extension, because of writer define like solution as extensions, and we should respect three conditions. But in practical terms, we use normal ones, which is ACC, and that's because there are problems in practical terms. We change just no B by I mean the red one we change by the blue one, just to become normal default. And like that, we always have one extension, and that's proved by writer. And in this case, we use normal default logic, normal default in this practical case. Our contribution is about 3 blocks. I will say that. First of all, we had the functional power. The functional power was developed by Charles at Onira, and that represents the capabilities and the feature of the robot, or skills. In our case, skills means actions. In our case, another block is which is the most important part, the non-monotonic reasoning model. And I will explain a little bit more which each subset. And the arithmetic planning is that contains the very known FF algorithms. So right now I'm gonna show you the guidelines of our model. It's starting by observations. Observations come from a skill model or here, or functional model. And that's they are in the form of predicated logic. We have the estimation theory, delta is, and this theory helps us to extend knowledge about the situation captured by observation. And we can describe default behaviors too. For example, here, localization, we assume that by default, for example, the robot is local. It has a good localization. The second one is safety theory. The safety theory is all about emergency rules. For example, when the situation has a problem about temperature, problem about water leakage, well, this theory will apply very quick actions because of safety rules, and this is what model safety rules, the safety theory. And finally, we have the wall theory. The wall theory can change or cancel goals according to the information at a time. Essentially, that's the main goal of this theory. Because of the time constraint, I'm just wanna show you the block on the left, and just like information. This is the algorithm we implemented for the study, but I will summarize in this figure. We start for example from the functional part. Functional part send some informations to the non-monotonic block. So in here, two situations can derive. For example, an emergency. Because it's an emergency, we will apply a safety rule very quickly. If not, we estimate a state and a goal, and we go to the automated planning, and the automated planning will send all the action, all the segments of the actions to achieve this goal. But we evaluate this action, just the first action we will evaluate in the non-monotonic block. If there is no conflict with this action according to the situation, we apply the action, and the algorithm will turn to the end of the mission. And now this is a very abstract from the experimental procedure. First of all, we have three parts. First of all, the skills interface, or all the capabilities or feature of the robot, which embeds or embeds 3 data, 9 sources, and 10 skills or actions. And these skills are coded in Python and in Prolog using middleware, a ROS2 middleware. We use the automated planning FF algorithm, it's very known. And we use the fault theory, which is coded in Prolog. And we use 44 rules, which are 17 normal defaults and 27 exception or particular cases about the behavior. Here the simulation of results. Here we can see actually this is a normal mission, but we impose a problem here, a low quality localization. So and we see here the computation of non-monotonic solutions. On the bottom, on the top, we have the FF algorithm. We have some fluctuations, and well, it's just to know the behavior of the both algorithms. Now, this is a problem this is a normal mission, but we impose another problem, which is power supply problem. And the same, we plot the computation of non-monotonic reasoning and the computation of FF algorithm. The same, we some fluctuations, and we cannot see the difference, but in the next one, you can see the difference. And the plot here is the worst case simulation, or the worst case scenario. Here the worst case scenario is when the robot has to do 32 transits. This is the worst case scenario. And what happened here is well, we see that non-monotonic reasoning computation time is constant or quasi-linear. And that, while the FF algorithm has like a exponential response. So this is not good, but this is a problem. This is a very known problem from the FF algorithm. Which is important here is the computation time of the non-monotonic part is constant. It's almost constant. We can see on the other side, on the right side, fluctuation also the same from the FF algorithm. But the important thing here is the computation of the goals from the non-monotonic reasoning part is almost constant. So this is quite a good signal, because the algorithm, no matter how rules we put inside, the behavior of the computation will be constant. And finally, the conclusions. Well, we show we show that a new decision-making architecture based on non-monotonic reasoning, which has the capability to manage safety rules and world reasoning. Also, you can say that the full logic is a very powerful tool for solving problems that have not monotonic behavior. We model, we prove some guidelines for use and in another application. And the last but not least, which is very important, practical verification of model complexity, which is a quasi-linear or constant, with 44 rules. And now we are turning to multi-agent systems, and why not autonomous agent with these guidelines I present you. So thank you for your time, and thank you for your attention too.